Welcome again in my online session on modern spectroscopic techniques of analysis. Into this session, we will talk about nuclear magnetic resonance spectroscopy. Now, this NMR spectroscopy is a kind of absorption spectroscopy. Earlier, we discussed UV visible absorption spectroscopy, IR absorption spectroscopy. In UV visible spectroscopy, electrons are involved in absorption. In IR spectroscopy, particular functional group absorbs due to its natural vibrational frequency. But here, in NMR spectroscopy, it is absorption spectroscopy, but here the major difference is nucleus of that atom is involved in the absorption. Now, when electrons are involved in absorption, electrons can move from their ground state to excited state because electronic orbitals are available in the atomic structure. If you look at atomic structure, atom contains nucleus surrounded by electronic orbitals, and nucleus is positively charged species and electrons are negatively charged species. When electrons involved in absorption, they shifts from their lower energy orbital to higher energy orbital. But when nucleus is involved in absorption, there is no such orbitals available for nucleus to shift after receiving energy. So here it needs application of strong magnetic field so that it can split energy levels of the nucleus based upon their spin quantum number, and if nucleus is kept in a strong magnetic field and if it is exposed to radio waves, that nucleus at particular point of applied magnetic field absorbs radio waves and shifts to the higher energy state. This is known as that nucleus is in resonance with a radio waves provided. So the name nuclear magnetic resonance spectroscopy. So here energy source used is of radio waves. Magnet is used to split energy levels of the nucleus and to have a spinning motion in the positively charged nucleus, and this is how the behavior of nucleus in magnetic field with radio waves is recorded. That is what is phenomenon of NMR spectroscopy. Now, how this NMR spectroscopy is used? What type of nucleus or what type of atoms are involved in absorption, or what type of atoms are NMR active? That will be governed by the spin quantum number of that atom. Now the spin quantum number should be non-zero. If spin quantum number is 0, there will be no splitting in the energies, and such atoms are NMR inactive. Now if you look at this, the spin quantum number will be governed or will be decided by its mass number and atomic number. What is atomic number? That is number of protons or number of electrons, because both are equal in number. And a mass number is a number of protons as well as number of neutrons, because both have one mass units. Okay, so there should be if atomic number and mass number both are even in an atom, such an atom have spin quantum number 0, and such atoms are NMR inactive. Where if atomic number is odd or even and mass number is odd, in this case the spin quantum number is half integral. And if mass number is even and atomic number is odd, a spin quantum number is like 1, 2, 3, 4, the whole number. So this could be NMR active, whose spin quantum number is non-zero. But most preferred atoms in NMR analysis are atoms with half spin quantum number, that is 1/2. These are the nucleus of atoms whose spin quantum number is half. Hydrogen 1, carbon 13, fluorine 19 and phosphorus 13. These are with half spin quantum numbers and these are NMR active. If we study this proton, it is known as proton NMR studies. If C13 carbon is involved, it is C13 NMR likewise. Okay. Now if we consider isotope of this carbon, regular isotope, that is C12. In the C12, its 12 mass number is even, that is 12. Atomic number of carbon is 6. So in case of C12, mass number 12, that is even, atomic number 6, that is again even. So C12 is not NMR active. But in contrary, C13 is NMR active because in C13 its atomic number is 6 but mass number is 13 because it has 6 protons and 7 neutrons. That's why a mass number is 13 and it is NMR active with half spin quantum number. Now these are the values for this particular atoms, or magnetic properties of these atoms are quoted here. So one must know these values because in case of that MCQs type questions, there may be chance that such values or questions on such values may be asked. So one should know the gyromagnetic ratio, isotopic abundance, relative sensitivity and absorption frequency of particular NMR active nuclei. Now, how this phenomenon takes place? What is the principle on that NMR is based? Now here what I already told that in NMR, nucleus of an atom is involved in the absorption. Now if here we consider the hydrogen atom, the nucleus of hydrogen atom contains only a proton. That's why hydrogen atom is called as a proton. All other atoms or nucleus of all other atoms contains proton as well as neutron. There is only one atom, hydrogen, whose nucleus only contains proton. There is no neutron in the nucleus. That's why hydrogen atom is called as a proton. And it is a positively charged species. So nucleus of any atom is a positively charged species because it contains proton, and whole atom is neutral because whole atom is nucleus as well as electrons, and whole atom contains equal number of protons, that is positively charged species, and electrons, that is negatively charged species. So whole atom is neutral but its nucleus is positively charged species because it contains only charged species, that is proton, which has positive charge. So when such a nucleus, when any charged body kept in a strong magnetic field, it will have a precessional motion, or it will have a circular motion. How circular motion is? You can imagine a top, a spinning top. When top is spinning, it has a circular motion around its own axis. That is known as a spinning motion. That top is spinning around its own axis. at the same time the axis of the top is not static. It also has some circular motion with a definite frequency. That circular motion of that axis around which top spins, it is known as a precessional motion. The circular motion of axis of the top is a precessional motion, and it has a frequency with which it is precessing. It is called as a precessional frequency. Now only spinning top have a precessional motion. If top is not spinning, it will fall down. There is no precessional motion, there is no circular motion of the axis of the top when it is not spinning, because if it is not spinning, it will fall down. So only spinning nucleus have a precessional motion, and nucleus can spin only when it is kept in a strong magnetic field, because it is a positively charged species. As any charged species in a strong magnetic field will have a spinning motion. So here, as this precessional frequency is governed by a strength of applied magnetic field. A precessional frequency will be directly proportional to the strength of applied magnetic field. If we increase applied magnetic field, precessional frequency will increase, because spinning frequency will also increase. And a nucleus will absorb radio waves when its precessional frequency matches with frequency of the radio waves. Because here during estimation, you can see that the frequency of radio waves is kept constant, and a strength of applied magnetic field is slowly increased. So with increasing strength of applied magnetic field, precessional frequency will also increase. And when a precessional frequency of a particular proton, when it is equal to a frequency of applied radio waves, then it is said that that proton is in resonance with radio waves and it absorbs that radio waves. So the name nuclear magnetic resonance, because in the magnetic field that nucleus is in resonance with the radio wave supplied and it absorbs. So this is how nucleus absorbs the radio waves and record. Now after absorption, you can see that the nucleus, this is a parallel and this is anti-parallel state. A nucleus, when it is in resonance, it absorbs radio waves and go to the anti-parallel, and energy absorbed will be equal to delta E, that is delta E is equal to h nu. This is energy of absorbed radio waves, and a shifting of protons from lower energy state to higher energy state takes place. Now this is a typical instrumentation or instrumental components of the NMR. You can see, as I already told, that this is, you can say, a sample which contains proton or hydrogen atoms that are involved in absorption. It is kept in a strong magnetic field. The magnetic field is applied to this, and it is connected with a radio transmitter and a radio waves detector, RF transmitter and RF receiver. It goes to the detector. So radio waves are provided to the sample, and after that they are received back to the detector. Now this frequency of supplied radio waves is kept constant. That is, you can say, a monochromatic radiation. Radio waves of fixed frequency, a fixed wave number, that is provided to this, and it is kept in a strong magnetic field. Gradually magnetic field will be increased, so that the protons in this sample will have a spinning motion and a precessional motion too, because a spinning proton will have a precessional motion that we have seen. As we go on increasing the applied magnetic field, the precessional frequency will also increase, and when the precessional frequency becomes equal to frequency of radio waves, it will absorb. And that moment, the absorption will be recorded and amount of transmitted radio waves will be decreased. That deflection will be recorded as absorption and it will be recorded as a peak on the record. Okay, this is how it takes place. Now suppose still we increase the strength of applied magnetic field, then earlier proton which was in resonance, whose frequency now will be different than the radio waves, so it will be out of resonance. But another proton in the sample may have in resonance with radio waves because its precessional frequency is equal to the frequency of radio waves. In that case, another proton may absorb and it may show another peak. This is how different protons or different hydrogen atoms in various chemical environment, those who are there, they shows different peaks. That is what is, you can say that, a chemical shift. Now how it happens? What is responsible for chemical shift? This is one of the important parameter in NMR to identify what kind of functional group is present in a particular molecule. See here, there are two major parameters which are used in NMR for identification of the molecule or identification or illustration of the structure, that is chemical shift and spin splitting. This chemical shift will talk about what is the functional group present, and chemical spin splitting will talk about how these different functional groups are attached to each other. Okay, so this typical functional group have a typical chemical shift value. How it is, I will tell. And spin splitting will talk about who is a neighbor. So once you know a member and neighbor, we can connect each other, how they are connected to each other, and we can draw a structure. Now here it's a typical example of, say, ethanol, CH3CH2OH. This is the delta value, you can say that. Now this hydrogen, now this chemical shift is because of shielding and de-shielding. How it happens? What is shielding? A protection of that nucleus because of some secondary magnetic field generated. And secondary magnetic field generated because of the electrons around. When we consider a hydrogen atom, its nucleus is a proton. At the same time, that hydrogen atom is surrounded by electrons. When that hydrogen nucleus is spinning, it is showing magnetic property. At the same time, because electrons surrounded are also charged pieces, they will also have a circular motion. They will also generate a secondary magnetic field, and that secondary magnetic field generated by electrons around, if it is opposing the applied magnetic field, it protects the nucleus of the hydrogen. That is called as shielding. And if that electron density is reduced, it de-protects the nucleus, that is de-shielding. So this shielding and de-shielding is responsible for the chemical shift. If you look at this, the hydrogen atom connected to oxygen in OH group, this hydrogen nucleus is de-shielded as compared to this CH2 or as compared to this CH3 hydrogen atoms, because the OH hydrogen is directly connected to oxygen, which is electronegative, and this oxygen pulls electron density of hydrogen around. Because electron density around this hydrogen is reduced, it is de-shielded. So it will show chemical shift value at a lower applied magnetic field. So delta value will be here. Delta value will be more because the applied magnetic field will increase from this to this side, and delta value will increase from this to this side. This is a delta value of internal standard. It is considered 0 because it is appearing peak at highest applied magnetic field, that is upfield. Because all these 12 protons of tetramethylsilane, that is internal standard, are shielded. So they need higher applied magnetic field and delta value of that is considered 0. But here if you look at this, H is connected to electronegative oxygen, so it is de-shielded and it shows peak at lower applied magnetic field or higher delta value. And compared to this, it is comparatively less de-shielded than this. So CH2 peak will be at some higher applied magnetic field, and CH3 peak will be at still higher applied magnetic field, because CH3 peak is shielded. CH3 hydrogen atoms are more shielded than OH, because CH3 hydrogen atoms are far away from electron withdrawing oxygen. CH2 is little close to oxygen. H is directly attached to electron withdrawing oxygen, which is more de-shielded than this and than this. Okay, so this is how, because of shielding and de-shielding, shift in peaks observed, and that is a chemical shift. So here electrons or electronic density around that nucleus of that atom is responsible for chemical shift. Any neighbor who is altering the electron density around the nucleus of that atom, that will cause shielding and de-shielding and ultimately cause a chemical shift. Now I already told that internal standard used is, this is a tetramethylsilane. If you look at the structure of this, it is having 4 methyl groups, so it has total 12 hydrogen atoms. All these hydrogen atoms are in same chemical environment, because CH3 is connected to Si, this is connected to Si, this is connected to Si, this is again connected to Si, because all 4 CH3 groups are connected to same Si, and all 12 hydrogen atoms are in same chemical environment. Because they are in same chemical environment, they shows sharp peak at a fixed applied magnetic field, because all 12 hydrogen atoms of tetramethylsilane will be in resonance with radio waves at a particular applied magnetic field. So it shows a sharp peak, and it is assigned as a 0 delta value, and from that right to left a delta value increases, and from left to right magnetic field, applied magnetic field increases. Okay, now this is, you can say, a delta scale. This is a tetramethylsilane, peak of tetramethylsilane, where a delta value is assigned 0, delta value is expressed in the ppm, it is assigned 0, and from right to left you can see here delta value increases. Okay, and a magnetic field increases from this to this side, and 60 megahertz is a frequency of radio waves. 300 megahertz is again the frequency of radio waves which is used in that instrument. Here in the instrument, frequency of radio waves is kept constant, and there may be, you must have heard that 60 megahertz NMR instrument, 300 megahertz NMR instrument, 400 megahertz NMR instrument, or nowadays 600 megahertz NMR instrument. What it says, that it means the radio waves which are used in that particular instrument are of maybe of 60 megahertz or 300 megahertz or 400 megahertz or 600 megahertz. Accordingly, that instrument is so called. And in such instruments, a magnetic field is altered. Okay. Now, if we look at this again, a typical protons will have a typical delta values. sp2 carbon, OCH3, OH, these delta values are typical. Now there will be alteration in the delta values based upon what substituent is connected. or who is its neighbor, where this proton is attached, by what kind of bonding it is attached. So that will, or that may alter the delta value, and that will help in identifying the neighbor and elucidating the molecular structure. Now this is the spin-spin splitting. This is another factor that gives information about who is a neighbor of that functional group. And the spin-spin splitting will be decided by number of protons on adjacent carbon. I am saying on adjacent carbon. If there is a heteroatom, then this spin-spin splitting effect will not be observed. If you take example of this again, CH3, CH2, OH. OH peak, this is peak for OH. It is a singlet. There is no splitting in this peak because this H is attached to a heteroatom O. So no question of spin-spin splitting here. Now this CH2 peak, if you look at this CH2 peak has split into 4 peaks. 1, 2, 3 and 4. This CH2 peak has been split into 4 peaks because its neighbor or its neighboring carbon contains 3 hydrogens. Number of hydrogens on the neighboring carbon plus 1. That will be the splitting. Now the CH2 peak is splits into 4 because its neighboring carbon contains 3 hydrogen. 3 plus 1, 4. So 4. Now the CH2 is again connected to OH, but here this side a neighbor is not carbon. It is OH. So it will not affect on the splitting of CH2. Now this is the CH3 peak, you can say, and the CH3 peak will split into 3 because the CH3 is connected to carbon bearing 2 hydrogens. So 2 plus 1, 3. So CH3 will split into 3, CH2 will split into 4 because of number of protons on a neighboring carbon. So in short, for spin-spin splitting, number of protons on neighboring carbon are responsible, and for chemical shift, electronic density around that nucleus is responsible, or electron density in that particular atom is responsible. Now one more factor, that is J. The spacing between these 2 split-in peaks. Suppose here you can say the 3 split-in peaks, the distance between this and this peak and this peak, also a distance between these split-in peaks also will be same, and that is in the hertz, that is in the frequency units, that is called as a J, or a coupling constant, and the J value of a particular compound is fixed. So from that J value also we can identify the molecule. Okay, so this is a J value, where this is the spacing distance between the split-in peaks in hertz unit, frequency units, is known as spin-spin splitting constant, or a J value. Now this, how the splitting takes place. The splitting takes place as per this. Suppose a neighbor, it has 0 number of protons, there will be a single peak, that is a singlet. If a neighboring carbon contains 1 proton, it will be doublet, and 2 peaks will be of same intensity, 1:1. If it is doublet, both peaks will be of same intensity, you can see like this. So if a neighboring carbon contains 2 hydrogens, it will be a triplet, and intensities will be like this, 1:2, 2:1, right? A central will be intense and side 2 will be of equal intensity. So a triplet. Now 3 quartet, 1:2, 3:3. 4 it is pentet, 6-let, septet, based upon number of hydrogens on a neighboring carbon. And this, how it is constructed, 1, 1, 1, 1, 1 plus 1, 2 and 1. 1, 1 plus 2, 3, 2 plus 1, 3, 1. Likewise, go on addition these, this triangle will be generated. So this is how the intensities of a splitting peaks can be generated, and it shows either singlet, doublet, triplet, quartet, pentet or multiplex, you can say, based upon number of protons on a neighboring carbon. So by this, with the help of chemical shift and spin-spin splitting in proton NMR, we can find what is functional group, how it is arranged. So by combining this and by knowing its molecular weight from mass spectroscopy, also having support of IR spectroscopy for confirming the functional groups, together with all this data, we can reach to the structure of compound after spectral analysis. So if we have a spectral data, all spectral data like IR, NMR, C13 NMR, mass, elemental analysis, then by this data together we can elucidate the molecular structure. Earlier, before the spectroscopic studies, this elucidation of molecular structure was done by chemical degradation method, and it was tedious, time consuming and costly affair. We have to make some known chemical reactions, break down it into smaller fractions, identify that fractions and reconstruct back that fractions to the original structure. See how tedious it is. But by knowing all the spectral data, we can immediately reach to the structure of atom. This is the glory of spectroscopic analysis. This is how it is used in elucidation of molecular structure. Now this is a typical NMR spectrum. You can see NMR spectrum of this compound. See here CH3. These 3 protons are in one chemical environment. This CH3, these are in different chemical environment, and CH2 is again in different chemical environment. So all 8 hydrogen atoms in this structure, they are divided into 3 chemical environments, because this CH3 is directly attached to oxygen, this CH3 is attached to carbonyl group, and this CH2 is attached to another carbonyl group. So these are in different chemical environment, because electron density around these protons will differ because of their adjacent group. Okay, now if you look at this CH3 will be more de-shielded because it is directly connected to O. So its delta value will be higher. De-shielding gives higher delta value, lesser magnetic field and higher delta value. Now comparative to this, if you look at, this is again attached to both carbonyls. It is in between 2 carbonyl groups. Carbonyl groups are also electron withdrawing, so they will also reduce electron density around this. So the next to this is CH2, a delta value, and this CH3 is comparatively shielded with than CH2 and CH3. If you compare within this is more shielded than this and than this. So you can have this CH3 peak here at lower delta value, CH2 peak at little higher delta value, and this CH3 peak again at little higher delta value. Then all 3 peaks are singlet, because there is no neighboring carbon to this. Here again there is neighboring carbon but no hydrogen to the neighboring carbon. Here on neighboring carbon there is no hydrogen. So there is no question of spin splitting. So no splitting, so singlets. All these 3 peaks, chemical shift peaks, are singlet. And this is the internal standard TMS at highest applied magnetic field, so delta value is 0. It is assigned, and all others delta value are compared with internal standard, that is tetramethylsilane. So this is how typical NMR spectra looks like, and from this all spectroscopic data we can go for elucidation of molecular structure. Thank you.